For almost all of human history, no laboratory had held an identified sample from the moon's far side. Then a small capsule returned with nearly 2 kilograms of gray soil. Those grains carried ancient lava, impact glass, and a faint record of a vanished magnetic field. The hidden hemisphere is not a place of endless darkness. Sunlight crosses its mountains and crater floors. Its real difference is written in the ground. Welcome to cosmic drift. The room can soften while the familiar moon turns slowly away. The screen may dim, and the volume can settle just above a whisper. A quiet like or subscription helps these calm nights of science find another listener. Nothing here needs to be memorized. Attention may stay with the story or loosen whenever sleep arrives. The night will move from the moon's locked rotation to its first photograph, its deepest scar, its returning samples, and its radio hush. The answer can begin at once. What missions found was not an alien landscape hidden from every camera. They found an older-looking hemisphere with thicker highlands, fewer dark lava plains, and a history unlike the face seen from Earth. In June of 2024, Chang'e 6 brought part of that history home. Its return capsule settled onto grassland in Inner Mongolia. Inside waited 1,935.3 grams of lunar material. The amount would fit inside a modest food container. It was less than the mass of a large house cat. Yet no collection in any laboratory had come from this half of the moon before. Every earlier returned lunar sample came from the near side. Apollo astronauts collected their rocks there. Soviet Luna probes and China's Chang'e 5 also sampled the hemisphere facing Earth. The new grains came from the southern part of Apollo Basin. That basin lies inside a much larger wound called South Pole Aitken. The sampling ground sits more than 400,000 kilometers from many laboratories now studying it. Under a microscope, the soil is not simply gray. It contains pale plagioclase, several dark pyroxenes, bits of basalt, and almost 1/3 amorphous glass by one early analysis. Many grains are finer than a human hair. Some particles began as lava about 2.8 billion years ago. Other fragments record far older events. A set of ancient impact rocks has placed the Great Basin's formation near 4.25 billion years ago. That age reaches back close to the moon's youth. Earth's oldest surviving oceans may have been forming around the same broad era. On Earth, plate motion and water have rewritten most pages from that time. The moon kept more of them. It has no rivers to carry mountains away. It has no moving plates like Earth's, and almost no air to push dust across a continent. The lunar surface still changes. Small impactors arrive. Solar particles strike exposed minerals, while tiny collisions chip and melt the soil. Change there is slow and local. A footprint can remain crisp far longer than any human life. A basin can hold the outline of an impact for more than 4 billion years. This makes the far side valuable. Its relative lack of broad lava plains left old terrain exposed. Those battered highlands preserve impacts from the inner solar system's violent beginning. The phrase dark side often suggests secrecy. In astronomy, darkness once meant the unknown part, not a hemisphere without sunlight. The moon has an ordinary day side and night side, and both keep moving. At new moon, the far side is mostly in daylight. The near side then faces Earth in night. Around full moon, the arrangement reverses. A complete cycle of lunar lighting takes about 29.5 Earth days. A place near the lunar equator receives roughly 2 weeks of daylight. It then passes through roughly 2 weeks of night. Deep polar craters create an important exception. Some floors never receive direct sunlight because the sun stays low near the horizon. Those permanent shadows are small regions near the poles, not the whole far side. No telescope on Earth can look straight through the moon. That simple block of rock created the original mystery. The same block now offers shelter from Earth's radio noise. It also interrupts direct communication. A lander on the central far side cannot see Earth. Radio messages need a relay spacecraft positioned where both ends remain in view. China placed such bridges near the moon before the far side landings. Quietest carried commands around the lunar limb and returned scientific data. The name means Magpie Bridge, after a bridge in an old story. That bridge made a quiet landscape operational. Chang'e 4 landed there in January of 2019. Chang'e 6 followed with a more difficult descent, collection, ascent, rendezvous, and return. The returned soil has already corrected simple pictures of lunar history. Far-side volcanism did not end in one brief episode. Basalt fragments reveal activity, separated by well over 1 billion years. The grains also held evidence of an ancient magnetic field. Their minerals formed while the moon's internal dynamo still produced a field of several microteslas. That field was weaker than modern Earth's, yet stronger than some models expected for that late time. Another study found very little water in the source mantle, represented by the samples. A later thermal analysis placed that ancient mantle source about 100 degrees Celsius cooler than comparable sources beneath the near side. Each result adds another layer to the same question. The central question is how one small world became so uneven inside. A sphere should not have favored one face so strongly, yet its crust, chemistry, heat, lava, and surface shape all carry a broad east-to-west imbalance. The answer is not settled. A vast impact may have rearranged the interior. Heat-producing elements may have concentrated on the near side, keeping that hemisphere warmer and volcanically active. Earth's early heat may even have influenced the forming crust. Some models begin with tidal heating, or with a smaller companion moon merging slowly into one side. These ideas do not all fit together, and none has closed the case alone. That uncertainty is useful. It gives each mission a clear task. A rock can test a model that remote images cannot. The far side is fully mapped at orbital scale. It is not a blank patch kept from public view. Modern spacecraft have measured its height, gravity, chemistry, temperature, and reflected light. Mapping is not the same as touching. An orbital color can suggest a mineral, A grain in a laboratory can reveal its isotopes, crystal age, cooling path, and magnetic memory. The returned collection now lives under controlled conditions. Nitrogen-filled cabinets limit contact with air and moisture. Tools, containers, and work surfaces are checked, so an earthly particle does not become a false lunar clue. Only small portions leave the main store. A proposal must explain what will be measured and how much material the method consumes. Some tests preserve a grain, while others vaporize or dissolve it. This careful division extends the mission. A capsule flew for weeks, but the sample can support research for generations. Future instruments may read signals that present laboratories cannot yet separate. This is what was found. Not one shocking object, but a group of physical clues that changed the moon's biography. The hidden face became a laboratory rather than a rumor. The first clue to why it stays hidden is much older than any spacecraft. It lies in the steady rhythm between two rotating worlds. That rhythm keeps almost the same lunar face turned toward home. The moon moves around Earth while also turning around its own axis. Those two motions take nearly the same amount of time. One rotation lasts about 27.3 Earth days, and so does one orbit relative to the distant stars. This matching rhythm is called synchronous rotation. Tidal locking is the process that produced it. The moon does rotate, even though its markings seem fixed above Earth. A small experiment makes the geometry clear. One person can stand in the center of a room. Another can walk a circle around that person, while keeping the same shoulder pointed inward. After half a circle, the walker faces the opposite wall. After a full circle, every wall has passed before the walker. The body has completed one turn while completing one circuit. The moon does the same. Its near side keeps pointing roughly inward. Its far side keeps pointing roughly away. The lock is maintained by gravity, acting on a body that is not perfectly uniform. The moon's center of mass does not sit exactly at the geometric center. Slight differences in shape and density help stabilize the orientation. Earth does not hold the moon like a rigid handle. Both worlds orbit a shared center of mass. That point lies inside Earth, but not at its exact center. The motion gives Earth a small monthly wobble. Ocean tides respond to the same changing gravity. Friction in Earth's oceans transfers angular momentum outward and lets the moon drift slowly farther away. Laser measurements from reflectors on the moon track that retreat at a few centimeters per year. The present rate is not assumed to have stayed constant through all history. Continents, ocean depth, and orbital distance changed the tidal response. Long ago, the young moon probably spun faster. Earth's gravity raised a slight bulge in its body. That bulge did not line up perfectly while the moon was turning quickly. Earth's pull acted on the offset bulge. Internal friction converted some rotational energy into heat. The spin slowed over immense spans of time. Eventually, the rotation settled into the present resonance. The lowest energy arrangement kept the long axis of the slightly uneven moon aimed toward Earth. Similar locks occur among many moons in the solar system. The result is steady, but not perfect. The lunar orbit is slightly elliptical. Its speed changes as it moves closer to and farther from Earth. The rotation stays more uniform. Sometimes the orbit moves a little ahead of the turning surface. Sometimes it falls a little behind. The Moon's axis is also tilted slightly. An observer's position on a rotating Earth changes the viewing angle by a small amount. Together, these motions produce a gentle, apparent rocking called libration. Libration lets Earthbound observers see beyond the average edge. Across favorable times, about 59% of the lunar surface comes into view. No single night reveals all of that area. The remaining ground stays permanently beyond direct Earth sight. It includes most of the far side. Before spacecraft, even the finest telescope could only inspect narrow border regions. The edge itself is called the lunar limb. Mountains there rise as bright points against space. Valleys make small notches in the curved outline. Early astronomers used those details to estimate topography. They could watch sunlight crawl across the visible face. They could chart craters, rays, mountains, and dark plains. Their maps stopped near the limb. That boundary was not political or technical. It was enforced by orbital geometry. The familiar side appeared dark in broad patches. Early observers called them Maria, the Latin word for seas. They are not water, but ancient plains of basaltic lava. Their shapes create the face imagined in the Moon. Oceanus Procellarum and the Great Circular Maria cover wide areas. Pale highlands rise around them. If the Moon did not rotate at all, every part would eventually face Earth during one orbit. The fixed face is proof that rotation is happening. The apparent stillness comes from matched motion. The same geometry shapes lunar time. The interval between one local noon and the next is about 29.5 Earth days. It is longer than the sidereal rotation because Earth and Moon both move around the Sun. During that local day, shadows change slowly. A boulder can cast a long black line for hours. The line shortens over Earth days rather than minutes. At local sunset, the ground loses heat into space. With almost no atmosphere, warmth cannot be carried from the day side. Night spreads cold across the regolith. The far side receives the same sequence. It is bright for long stretches and dark for long stretches. Its name describes direction from Earth, not lighting. Tidal locking does not protect it from impacts. Earth covers only a tiny part of its sky, and gravity bends some incoming paths. The broad crater difference comes mainly from resurfacing history, not from Earth acting as a shield. The far side is more densely cratered because less lava later covered its scars. The near side suffered impacts too. Dark basalt buried many ancient marks under smoother plains. The locked orientation did influence the Moon in deeper ways. Tides once kneaded its interior more strongly. The young Earth filled a large part of the lunar sky and may have warmed the near side by radiation. Scientists test whether such early effects could help explain the hemispheres. Models must match the crust's thickness, the distribution of heat-producing elements, and the timing of volcanism. A pleasing story is not enough. Gravity data now show that the imbalance reaches below the surface. The near side responds to Earth's monthly tides differently from the far side. That difference implies a warmer region in the deep mantle. The match between spin and orbit also defines communication. At the center of the near side, Earth hangs almost fixed in the sky. At the center of the far side, Earth never rises. A human standing there would see the sun move over many Earth days. Stars would cross the black sky. The blue planet would remain below the horizon. Near the boundary, Earth could rise and set because libration changes the angle. A relay above the moon can also see over the limb. Its orbit turns an impossible direct link into two ordinary radio paths. This geometry gave the first far-side explorers a design problem. It also gave radio astronomers a protected region. The same rock that blocks commands from Earth can block television carriers, radar, and other artificial noise. The balance has a quiet precision. No motor keeps the moon aligned. No correction burn resets its face. Gravity and old friction produced the rhythm, then the orbit carried it onward. Every lunar month repeats the alignment, while small librations reveal changing slivers along the edge. Long before either use became possible, engineers had to see the ground. A camera would need to pass behind the moon, expose film, develop it in flight, scan the image, and transmit a weak signal home. That improbable chain became Luna 3. In October of 1959, a small Soviet spacecraft entered the region beyond direct Earth view. Its name was Luna 3. It carried no digital camera because practical digital space imaging did not yet exist. The craft used photographic film. A dual-lens camera made broad views and narrower detailed views. The film then moved into a tiny automatic laboratory inside the spacecraft. Chemicals developed and fixed the images. A scanner converted light and dark areas into an electrical signal. Radio sent the signal back when the craft regained a usable line to receiving stations. The method joined a camera, darkroom, fax machine, and deep space transmitter. Every part had to work without repair. The spacecraft also had to know which direction held the moon. Luna 3 carried photocells and gas jets for orientation. It turned its camera toward the sunlit far side on October 7th. The viewing angle included about 70% terrain unseen from Earth. The pictures were faint and noisy. Their contrast was low. Transmission weakened the detail further. Yet the main shapes survived. A hemisphere expected to hold broad, dark seas looked surprisingly pale. Craters crowded much of the ground. One dark oval received the name Mare Moscoviense. Another feature became Tsiolkovsky crater, with a dark floor and a bright central peak. The broad far side held far fewer Maria than the known face. The images turned an abstract hidden half into named geography. A map followed in 1960. Later missions corrected positions and added detail, but the first revelation remained. The contrast was not subtle. The visible hemisphere carries wide black plains that can be seen without a telescope. The new hemisphere appeared almost entirely highland terrain. Scientists now knew that the moon was globally uneven. The difference demanded a history. Lava had flooded one side much more than the other, and the reason was unknown. Luna 3 could not answer. Its photographs lacked fine resolution. It had no instrument for measuring rock chemistry or gravity. The mission did something more basic. It replaced an empty region with testable features. Future spacecraft could aim at real basins and craters. The first frames also showed the limits of language. Dark side had become a familiar phrase, but the photographed land was brightly sunlit. The name could no longer be taken literally. As better cameras arrived, the early blur gave way to structured terrain. The Soviet Zond missions and American lunar orbiters photographed more of the surface. Apollo crews later observed it with human eyes. Modern maps now resolve objects smaller than Luna 3's broadest smudges. Laser altimeters measure elevation by timing reflected pulses. Stereo images turn changing camera angles into terrain models. Spectrometers sort reflected light by wavelength. They reveal variations in iron, titanium, and mineral groups. Thermal instruments watch the ground cool through the long lunar night. Twin spacecraft from the Grail mission measured the moon's gravity. Tiny changes in the distance between them revealed mass below. The method mapped crust and basins on both hemispheres. The Lunar Reconnaissance Orbiter added images detailed enough to see landing hardware and narrow rover tracks. Its global products are public. The far side is no longer missing from lunar atlases. Still, the first photograph has a texture that modern precision cannot replace. It arrived as a gray radio-built image on paper. A whole hemisphere emerged line by line. The transmission took place in passes. Stronger signals allowed faster scanning. Weaker conditions required slower modes. Ground teams watched uncertain marks gather into a globe. Familiar limb terrain anchored the new features. Everything farther inward had never appeared on any human chart. The process resembles the way science often advances. A first result may be coarse. It can still reveal which questions deserve better instruments. The early image also required interpretation. Bright and dark patches had to be matched across frames with different distortion. Spacecraft position and camera angle were not known with modern precision. Cartographers used the visible limb as a reference. They projected the curved surface onto paper and estimated where unseen features belonged. Errors in one frame could shift a crater by many kilometers. Later photography did more than sharpen the picture. It corrected the coordinate system. Each improved orbit tied features to a global network of latitude, longitude, and elevation. Modern laser altimetry adds an absolute vertical scale. A crater is no longer only a circle of shade. Its rim height, floor depth, slope, and buried mass can be compared with impact models. Luna 3 showed the scarcity of Maria. Later geochemical maps revealed that heat-producing elements also concentrate unevenly. Gravity maps showed a thicker far-side crust outside the great impact basins. Each layer made the old photographic difference deeper. It was not only a surface pattern. The two hemispheres had cooled and erupted differently. The names added after 1959 carry the history of their era. Soviet scientists named features for explorers, scholars, and cities. International rules later standardized many names and revised others. Mare Moscoviense remains one of the rare far-side Maria. It sits as a dark patch within brighter highlands. Tsiolkovsky remains one of the most striking craters on the Moon. Its floor is flooded with dark basalt. A central mountain rises from the plain. From orbit, the contrast looks almost designed, though ordinary impact and lava made it. The far side also holds the enormous Apollo basin. It was named before the crewed landings and later became a region of special interest. Chang'e 6 would collect its samples inside that basin decades later. The first surveyors could not know this sequence. Their images offered only rough albedo, the fraction of light reflected by terrain. Brightness hinted at material, but it could not date a grain. No photograph can tell every part of a rock's history. It cannot directly reveal the isotope ratios locked in a crystal. It cannot measure the direction of an ancient magnetic field preserved during cooling. Still, an image preserves context that a loose grain lacks. The best lunar geology joins both. A sample carries chemistry, while its mapped setting explains which event may have placed it there. The far side story needed 65 years to unite those views. The first film showed where to look. The returning capsule supplied material that could answer why the view looked strange. The distance between image and sample took 65 years to cross. During that interval, the Moon's far side moved from photographed mystery to orbital laboratory. A robotic lander finally touched it, and another mission brought some of it home. Human eyes arrived much sooner. 9 years after Luna 3, 3 astronauts crossed behind the Moon. Their radios fell silent as the lunar body covered Earth. Apollo 8 reached lunar orbit on Christmas Eve of 1968. Frank Borman, Jim Lovell, and William Anders became the first people to leave Earth's immediate neighborhood. They were also the first to see the far side directly. Their spacecraft passed behind the Moon 10 times. Each passage removed Earth from view and blocked radio contact. For roughly 45 minutes, no ground voice could reach the cabin. Mission Control knew exactly why. Radio waves travel in straight lines through space. The Moon's solid body stood between the spacecraft and every receiving antenna on Earth. Silence was expected, but expectation did not make it ordinary. The crew had crossed a boundary no person had crossed. Behind them lay every city, family, and transmitter on the home world. Below lay terrain, first glimpsed only 9 years earlier. Sunlight struck crowded craters and pale highlands. The surface moved past at orbital speed. Apollo 8 photographed much of that ground. The crew described colors, shapes, and shadows. They also prepared and checked the engine burns that would keep them in lunar orbit and later send them home. When the spacecraft came around the limb, Earth appeared above the lunar horizon. William Anders took the color photograph later called Earthrise. A blue and white world hung over gray terrain. The picture was not made from the central far side. Earth cannot rise there. It appeared as Apollo 8 moved toward terrain with a line of sight home. Geometry gave the image its force. The living planet looked small beside the airless foreground. Clouds softened its surface, while every lunar edge remained sharp. Radio contact returned at nearly the same boundary. A signal found the deep space network again. Voices from Earth entered the cabin. For later Apollo crews, far-side silence became a repeated part of each orbit. It remained physically strange. No emergency instruction could cross the moon during those minutes. The spacecraft carried procedures for that isolation. Navigation and life support continued. The crew and onboard systems had to manage without immediate help. Robotic far-side missions solve the problem differently. A relay satellite stays in a position that can see the lander and Earth. Human flybys can accept a short blackout if the path is understood and systems remain healthy. 57 years after Apollo 8, another crew approached the hidden hemisphere. Artemis II launched on April 1st of 2026. Its Orion spacecraft carried Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. The crew named the spacecraft Integrity. Their mission tested Orion with people aboard on a nearly 10-day flight. It did not enter low lunar orbit or attempt a landing. Instead, the craft followed a free return path. Lunar gravity bent its course behind the moon and back toward Earth. That arc reduced the need for a large engine burn to come home. The main observation period lasted about 7 hours on April 6th. The crew looked through Orion's windows and photographed the changing surface. Long shadows revealed crater rims, ridges, and old lava. At 6:41 in the evening, Eastern Time, Earth slipped behind the lunar limb. The crew photographed the crescent planet above Ohm crater. 3 minutes later, radio contact ended. The planned blackout lasted about 40 minutes. The moon blocked the deep space network signals. Inside Orion, clocks and instruments continued while Earth remained below the horizon. During that quiet interval, Integrity passed about 4,067 miles above the lunar surface. It was moving a little more than 3,100 miles an hour relative to the moon. Relative to Earth, its speed was far greater. The crew also reached a record distance from Earth. The peak was about 252,756 miles above Earth's surface. That exceeded the distance reached by Apollo 13. From that distance, radio needed more than a second to travel each way. A spoken exchange could never feel perfectly immediate. During the blackout, even that delayed exchange vanished. The cabin did not become acoustically silent. Fans moved air. Pumps, electronics, and 4 people made a low mechanical room. The silence belonged to the link. No call sign arrived from Houston. No telemetry reached the ground until the spacecraft cleared the lunar edge. Orion continued on a trajectory shaped before launch and refined in flight. Its navigation combined ground tracking, onboard sensors, and star sightings. The moon's gravity supplied the broad turn home. Numbers on a flight display can sound clean. The view was made of harder textures. Vavilov crater cut across the rim of the older Hertzsprung basin. Oriental appeared near the lunar edge. Secondary crater chains crossed the ground in lines. Their indentations came from debris thrown outward by an ancient impact. At about 7:22, Earth rose again. A thin blue crescent cleared the opposite limb. The Deep Space Network reacquired Orion, and the gap closed. Later in the flyby, the Moon passed across the Sun from the crew's viewpoint. Totality lasted nearly 54 minutes. The dark lunar disk revealed a glow that scientists continued to examine in the images. The crew's observations were not a replacement for orbital instruments. Human vision can notice subtle color and texture, while instruments measure precise wavelengths and heights. The two forms of observation support each other. Artemis II saw some far-side regions under lighting unlike Apollo's views. The mission added fresh images of Ohm, Vavilov, Hertzsprung, and neighboring terrain. It also placed a new human scale beside the maps. 40 minutes is short beside a lunar night. It is long enough for 40 songs, a quiet meal, or the first part of a dream. In that interval, the crew carried every direct human presence beyond Earth's radio reach. Nothing supernatural caused the silence. A familiar law did. Solid rock blocked electromagnetic waves that could not bend far enough around it. That plain fact supports two very different feelings. For a spacecraft, the block is a risk to manage. For a radio telescope, it is a rare protection. The crew returned safely on April 10th. Their capsule splashed into the Pacific Ocean near San Diego. Images from the far side moved into public archives and science rooms. The new photographs included familiar scientific landmarks under fresh lighting. Long shadows emphasized terraces and central peaks. Color observations help teams compare rock units that can look equally gray in compressed video. Human eyes are not calibrated spectrometers. They are good at noticing relationships. A slight blue cast beside a brown-gray slope can guide later measurements and image processing. That collaboration between description and instrument echoes Apollo. A crew can name what seems unusual. Remote teams can then place the observation on a map and test it against data. The photographs show no boundary line between two kinds of moon. Near and far are parts of one continuous sphere, yet the terrain changes markedly as the view moves across it. The next question is geological. The broad, dark plains thin out as pale. Cratered highland takes over. Their uneven history must explain that change. The answer begins in a global ocean that no human ever saw. It was made not of water, but of molten rock. As that ocean cooled, the first lunar crust floated upward. Soon after the moon formed, much of its outer body was molten. Scientists call this stage the lunar magma ocean. It cooled over a long span, sorting minerals by density. Dense crystals such as olivine and pyroxene tended to sink. Lighter plagioclase crystals tended to rise. Their accumulation formed a pale crust, rich in anorthosite. That early crust still dominates the highlands. It reflects more sunlight than the dark basalt plains. Impact after impact later fractured and mixed its upper layers. The near side eventually changed on a grand scale. large impacts made basins. Molten basalt rose from below and flooded many low regions. Those lava sheets cooled into Maria. They appear smooth and dark from Earth. Their familiar arrangement helps create the imagined face in the Moon. On the far side, Maria cover only a small fraction of the ground. The exact boundary used in a map changes the percentage, but the contrast is immense. Roughly 1/3 of the near side is dark plain, compared with about 1% of the far side. The far side is not free of basalt. Mare Moscoviense, Mare Ingenii, and the floor of Tsiolkovsky show that lava reached the surface there. Chang'e sheiks also sampled a far side basalt plain. The difference is abundance. Near-side volcanism resurfaced broad regions. Far-side eruptions stayed more limited and scattered. Crustal thickness is part of the explanation. Data from Grail suggest near-side crust commonly around 30 to 40 kilometers thick. Far-side highlands can approach about 60 kilometers in some models. Thicker crust makes a longer barrier for magma. An impact may crack it, but molten rock still has farther to rise. In the deepest basins, the crust can become very thin on either side. Thickness alone cannot explain every map. South Pole Aitken has thin crust and low elevation, yet it did not become a single vast mare. Chemistry and heat must also matter. The near side contains a province rich in potassium, rare earth elements, and phosphorus. The initials form the name creep. Several of those elements release heat through radioactive decay. Creep is not one pure mineral. It is a geochemical signature in rocks and melts. The name collects several elements that became concentrated in late magma ocean liquid. Thorium maps from orbital gamma-ray instruments help trace this province. High concentrations cluster strongly on the near side. Far side highlands generally contain less. The distribution resembles a stain left by the last liquid in a cooling mixture. Later impacts and volcanism moved parts of it. The surviving map still points toward uneven early sorting. This Procellarum creep terrain covers a broad near-side region. It overlaps much of the hemisphere's long volcanic history. Extra internal heat could keep mantle rock capable of melting for longer. Remote sensing first mapped the chemical imbalance. Returned samples showed what some of those rocks contain. Grail later added a view of the deep response. Its twin spacecraft were called Ebb and Flow. They orbited one behind the other. Radio measured the changing distance between them with extreme precision. When the leading craft passed over extra buried mass, gravity pulled it slightly ahead. The separation changed. The trailing craft then felt the same pull. Repeated measurements produced a global gravity field. Combined with topography, that field constrained crustal thickness and density. It also exposed rings, faults, and buried basin structures. The map showed that the upper crust is highly porous. Billions of impacts shattered it. Empty cracks and broken rock reduce its bulk density. Porosity changes how scientists convert gravity into thickness. A denser assumed crust produces one boundary depth. A more porous crust produces another. This is why thickness maps come in models rather than one perfect number. Their strongest value lies in broad patterns. Far-side highlands stay thicker across reasonable assumptions. Local exceptions are equally useful. Large basins thin the crust sharply. Comparing those exceptions shows whether lava followed the easiest paths or also required extra heat. This porous shell can be imagined as a deep stack of damaged stone. It is not loose dust all the way down. Fractures become less open under pressure. The broad asymmetry survives beneath those local scars. In 2025, researchers used GRAIL data to study the Moon's monthly tidal response. The near-side mantle deformed differently from the far-side mantle. Their model indicated a deep near-side thermal anomaly of roughly 100 to 200 kelvins. Warmer rock is slightly softer and responds differently to tides. This offered the first clear gravitational sign of the long-proposed temperature imbalance. Later, Chang'e 6 sample work reached a related result from actual minerals. Basalt from the far side formed from a mantle source about 100 degrees Celsius cooler than near-side comparisons. Two methods were reading different pieces of the same broad pattern. Heat affects more than lava. It changes how a body cools, contracts, and carries elements. It can influence where deep moonquakes occur. The moon is not split into a hot half and frozen half today. Both interiors are cold compared with their molten youth. The measured difference is a residual imbalance inside an already cooled world. How that imbalance began remains open. One model starts with a giant impact on the near side. The event redistributes crust and brings heat-producing material toward one hemisphere. Another model considers Earth's radiation when the moon orbited much closer. The hot young Earth filled a large area of the lunar sky. Its warmth may have delayed crust formation on the near side. Tidal heating offers another route. Uneven flexing in an early eccentric orbit could distribute heat asymmetrically. A slow collision with a former companion moon has also been modeled. Each idea must reproduce several facts at once. It must explain the crust, lava, creep distribution, deep temperature, and basin record. Matching only one feature is not enough. The visible difference can therefore be read as a coupled system: crust-controlled ascent, heat-controlled melting. Impacts opened pathways and made low basins. Chemistry controlled how long the mantle could keep supplying melt. The final Maria pattern emerged from all four. This is why the far side samples matter. A chemical ratio can reject a thermal history. An age can place one event before or after another. The two faces are different, but neither is original and untouched. Both have endured impacts, lava, radiation, and dust. The far side simply preserves more ancient highland at the surface. Basalt changed more than color. A lava flow filled low topography and buried older craters. Later craters then formed on a new surface whose clock started at cooling. Scientists count those younger craters to compare lava units. Fewer superposed craters usually suggest a younger surface. Returned rocks convert the relative order into calendar ages. Near-side Maria record many separate eruptions. Their edges overlap like dark sheets of wax. Some flows traveled through channels and tubes before cooling. Far side basalt plains are smaller, so old crater populations remain easier to see across broad highlands. The view looks crowded because resurfacing removed fewer marks. It does not mean every far side impact occurred earlier. Elevation adds another contrast. Far side highlands sit higher on average. The moon's center of figure and center of mass are offset, and the crust carries broad variations. From orbit, a low sun turns those variations into long shadow. At full overhead light, the same terrain can look flatter. Topography comes from laser timing rather than shade alone. Anorthosite gives the highlands their pale tone. Its plagioclase reflects more visible light than iron-rich basalt. Space weathering modifies both, but the original mineral contrast remains. The far side is therefore not a uniform white shell. Dark mare patches, bright young rays, glassy impact melt, and weathered highland form a complex surface. The two hemisphere summary is a map-scale truth, not a rule for every crater. Any origin model must preserve that local complexity. A global temperature difference cannot predict each small eruption. Local fractures, basin depth, and source composition decide the final path. Its largest structure breaks every simple rule about preservation. South Pole Aitken removed and melted an enormous volume of crust. The basin became a window into early impact history. South Pole Aitken is not a neat circular crater with one bright rim. It is a vast, worn basin spread across the southern far side. Its outline stretches roughly 2,500 kilometers. That distance is close to a flight from London to Athens. Placed on Earth, the structure would cross several countries. On the Moon, it covers a major part of one hemisphere. Its floor lies many kilometers below surrounding highlands. NASA summaries place the average depth near 10 kilometers. Different studies define its edges and deepest points in different ways. The basin formed when a large body struck the young moon. The impact compressed, melted, and excavated crust. It may also have involved material from the upper mantle. No surviving instrument watched it. Scientists reconstruct the event from topography, gravity, mineral maps, and rocks. Computer models test impactor size, speed, angle, and internal structure. During the first instant, rock behaved unlike a familiar cliff. Pressure rose so high that solids compressed and flowed. A shock front moved faster than ordinary cracks. Behind that front, material expanded, melted, and accelerated outward. The temporary cavity was deeper and steeper than the final basin. Gravity then pulled walls inward and lifted deeper material. At this scale, collapse continued after the projectile had disappeared into vapor, melt, and fragments. Rings and faults spread far from the center. Later impacts blurred many of those original boundaries. The basin is among the largest well-preserved impact structures known. It is the largest and oldest recognized basin on the Moon. Calling it the largest scar in the whole solar system would go beyond the evidence. The outer shape is elliptical rather than perfectly round. Later craters cut across it. Lava flooded several inner basins, while other regions remained pale. At depth, Grail found an excess of mass beneath part of the structure. The anomaly may include dense mantle material or metal left by the impactor. No single source model has won. The impact produced a melt sheet. Molten crust and perhaps mantle material pooled and differentiated as it cooled. Later impacts excavated fragments from those layers and scattered them again. Chang'e 6 samples now give this story a laboratory anchor. Researchers dated ancient Norite fragments near 4.25 billion years. Their context supports that age for the basin-forming impact. Norite is an igneous rock rich in plagioclase and low-calcium pyroxene. Some fragments also contain olivine and tiny accessory minerals. Zircon-bearing grains preserve clocks based on radioactive decay. An age is never read from a printed label. Scientists measure parent and daughter isotopes in minerals. Known decay rates turn those ratios into time estimates. Impact heating can reset some mineral clocks and leave others partly unchanged. A date may record original crystallization or later shock. Researchers compare several isotope systems and textures to decide which event the clock represents. Zircon is especially useful because its crystal structure accepts uranium when it forms, but tends to reject lead. Lead produced later by decay becomes a built-in timer. Damage and later heating complicate the reading, so individual grains are checked closely. Several grains and several methods strengthen a result. Geological context matters too. A rock ejected by a later crater may have formed much earlier elsewhere. At the Chang'e 6 site, later impacts mixed local basalt with foreign highland material. Early analysis estimated at least about 13% non-local material in some sampled ground. That mixture is a complication and an opportunity. Local basalt records volcanism near the landing site. Foreign fragments may sample distant crust or old basin melt. One scoop can hold several chapters with different origins. The Great Basin also contains Apollo Basin, roughly 490 kilometers wide. Chang'e 6 landed on a basalt plain within its southern region. The nested structures resemble scars inside a much older scar. Before the samples returned, crater counts estimated surface ages. Scientists counted impacts of different sizes and compared them with terrains dated by Apollo and Lunar rocks. Far side material provided a new calibration point. This matters far beyond one crater. Planetary surfaces without returned samples are often dated by crater density. The lunar clock helps estimate ages on Mars, Mercury, and other rocky bodies. If the age of a major lunar basin changes, models of early bombardment can change with it. The timing affects ideas about when large impacts declined. It also touches the conditions on early Earth. Earth was struck more often because it is larger and has stronger gravity. Almost all of those ancient terrestrial scars are gone. The Moon keeps a nearby record of the same population of impactors. South Pole Aitken is not a perfect archive. Later events churned its surface. Lava covered some ground, and ejecta from younger craters crossed the basin. Yet the overall structure remains. Gravity remembers where mass moved. Minerals remember when they crystallized. The basin may expose deep material, but that claim needs care. Orbital spectra have found minerals consistent with lower crust or mantle. Some candidate olivine-rich regions may instead be products of impact melt differentiation. An impact melt sheet can sort itself as it cools. Dense crystals sink and light crystals rise. That internal sorting may imitate layers once thought to come straight from the mantle. The distinction changes the basin's meaning. Direct mantle would sample the moon below its crust. Differentiated melt would sample the impact's own temporary magma body. Both are valuable. Only one supports a claim that the mantle lies exposed. Mineral chemistry and crystal relationships decide between them. Chang'e 4 found material interpreted as olivine and low-calcium pyroxene inside von Karman crater. Later studies refined the interpretation. Chang'e 6 fragments now let researchers test such orbital and rover readings directly. The difference between mantle and impact melt is important. Both can contain similar minerals. Their textures, trace elements, and isotope systems reveal how they formed. A dramatic phrase might say, "The impact tore the moon open." The physical story is quieter and more precise. Shock waves crossed rock, pressure rose, material melted, and excavation lifted deep layers. Some ejecta traveled hundreds of kilometers. Some fell back within minutes or hours. Fine vapor and melt cooled into glass. Over the next 4 billion years, smaller impacts broke that ground again. Solar wind altered exposed surfaces. The original basin became a layered field of old and younger events. The scale is easiest to feel from a map. The basin's long span is greater than the radius of the moon. A traveler crossing it for several hours each day would need more than 2 months, even without craters blocking the route. Its gravity field offers a second way to feel the size. A spacecraft passing overhead accelerates by a tiny extra amount. That pull continues across a region wider than many nations. Grail converted those accelerations into buried structure. A mass excess lies beneath the basin. The amount is vast, though its exact distribution depends on density models. One explanation includes uplifted dense mantle after the crust was excavated. Another allows metal from a differentiated impactor to remain at depth. Impact melt and later mantle adjustment may contribute as well. The basin floor also relaxed under gravity. Hot material flowed more readily soon after impact, while cooling made later deformation harder. The final shape records both violence and recovery. No intact projectile waits below like a buried coin. Shock broke and mixed the impactor with lunar material. Any remaining metal would be dispersed through a large subsurface volume. Future gravity data at lower altitude could refine the anomaly. Seismic waves crossing it would test density and temperature. A drill can only reach the shallowest layer, so several methods must build the cross-section. The basin's edge is equally informative. Ejecta thickness falls with distance. Rocks near the rim may come from different depths than material far outside. A well-planned traverse could follow that gradient. Samples from several positions would show how the target crust changed with depth. They would also reveal how later craters redistributed the original sheet. This work depends on ordinary labels and careful coordinates. A grain marked only far side loses the connection. A grain tied to a mapped boulder, ray, and unit can test an impact model. There is no road there. Slopes, loose regolith, temperature swings, and communication limits make every robotic meter costly. The basin's scientific size is matched by an engineering one. That challenge kept all early landings on the near side. A far side craft needed a bridge for radio, an autonomous descent system, and terrain chosen from orbital maps. Chang'e 4 was built to make that first contact. Chang'e 4 began with a satellite sent ahead. Chao launched in May of 2018. It traveled toward a region beyond the Moon, called the Earth-Moon Second Lagrange Point. The satellite did not sit motionless at that point. It followed a broad halo orbit around it. From there, antennas could see Earth and the far side landing region. The Moon remained below and ahead from the relay's viewpoint. Radio from Earth reached Chao. A second link carried commands down to the lander and rover. Data returned along the reverse path. Every message crossed two legs. The arrangement added delay and complexity, but it made the hidden ground reachable. Chang'e 4 launched in December of 2018. On January 3rd of 2019, it descended into von Karman crater. No spacecraft had landed softly on the far side before. The crater is about 180 kilometers wide. It lies within the South Pole Aitken basin. Its floor contains ancient impact material, later lava, and ejecta from surrounding events. The lander fell on rocket thrust. There was no air for a parachute. Cameras and navigation software compared the approaching surface with hazards. Near the ground, dust moved outward beneath the engine. The legs settled onto gray regolith. A ramp then unfolded. U-22 rolled down the ramp. The name means Jade Rabbit 2. The rover was about the mass of 2 adults and carried 6 wheels. Its mast held panoramic cameras. A spectrometer measured visible and near-infrared light. Ground-penetrating radar sent pulses into the soil and listened for returning echoes. The first radar profiles reached roughly 40 meters in useful early interpretation. They showed layers of fine regolith and coarser material. Buried blocks likely came from repeated impacts. Radar does not photograph an underground cavern. A pulse reflects where electrical properties change. Scientists turn travel time and signal strength into possible layers. The result depends on assumptions about the material. Dense rock, porous soil, and mixtures carry radio waves differently. Several models may fit one faint boundary. The profiles revealed a surface more transparent to radar than the Chang'e 3 site on the near side. That allowed deeper structure to appear. The ground was not one smooth blanket. One layer contained finer material near the top. Below it, stronger reflections suggested blocks and coarse ejecta. The pattern matched repeated burial rather than a single deposit. As the rover moved, radar built a narrow vertical curtain beneath the route. Each meter added a column. Joining the columns created a subsurface section. The curtain does not extend across the whole crater. It belongs to one traverse. Orbital images supply the wider setting, while the rover gives depth along its line. It held a stack of ejecta. Each nearby impact threw out fragments and dust. Later events buried earlier deposits. U-22 also examined unusual rocks. Spectra showed olivine and low calcium pyroxene in some material. Those minerals can form in the mantle, lower crust, or a differentiated impact melt sheet. Their presence supported deep excavation somewhere in the basin's history. It did not prove that bare mantle covered the rover's route. Sample return would be needed for a stronger test. The rover moved slowly. Lunar terrain punishes speed. A wheel must cross loose soil, sharp stones, slopes, and craters, while remaining within safe power and temperature limits. Wheel tracks also measure mechanical behavior. Their depth and slip reveal how firmly grains support weight. Engineers compare commanded motion with actual distance. The rover can turn in place, but every turn disturbs soil and spends energy. Route planners favor gentle arcs and safe slopes. A small, unseen crater can end a mission. Autonomy handles the final moments of some movement. Earth cannot steer each wheel in real time. Images return later for the next plan. One lunar day gives long sunlight. Solar panels can work for many Earth days. The following lunar night brings deep cold and no sunlight. U-22 folded into a protected sleep during those nights. Heaters kept critical parts within limits. The rover woke when sunlight returned. Its route bent around hazards. Each command was planned from images and delayed by the relay path. A modest drive could take an Earth day of analysis. The lander remained near the touchdown point. Its instruments included a low-frequency spectrometer and a neutron and radiation detector. The detector made the first systematic active dose measurements from the lunar surface. Cosmic rays arrive from outside the solar system. Solar events can add energetic particles. When those particles hit lunar soil, they can also create secondary neutrons and gamma rays. The Moon has no thick atmosphere to absorb the shower. It has no global magnetic field like Earth's. A future crew would need material shielding and warning systems. The far side did not remove that radiation. Its radio quietness concerns lower energy electromagnetic signals from Earth. High energy particles cross space from many directions. A small biological container on the lander carried seeds and tiny organisms in a controlled environment. A cotton seed germinated briefly. The experiment ended as the lunar night drove temperatures beyond its thermal design. The living sprout was inside a container, not rooted in lunar soil. It did not show that plants can grow exposed on the Moon. It showed how difficult even a sealed miniature environment can be. Outside, U-22 kept reading stone. Its cameras recorded tracks and shadows. The wheels disturbed a surface that had rested between recent impacts. Freshly exposed soil can look different from weathered ground. Solar wind and micrometeorites darken and alter grains. Rover tracks therefore become small experiments in exposure. The mission also tested the relay idea over years. Chang'e carried data beyond its original early operations. Its success became a foundation for a more demanding sample return. A rover can study only the line it travels. Its instruments must fit within mass and power limits. Laboratories on Earth can divide one grain among many machines. Even so, place gives the rover an advantage. It can inspect a rock before touching it. It can compare the stone with nearby soil and crater rays. The strongest program combines both scales. Surface observations choose the right material. Return laboratories read it with far greater precision. The first landing, therefore, changed the question. It no longer asked whether a far-side surface mission was possible. It asked which material deserved a trip home. Chang'e 6 targeted Apollo Basin, not the Chang'e 4 site. A new relay called Quietest 2 supported the mission. Its path and antennas were designed for several future lunar tasks. The landing zone offered basalt, basin ejecta, and unusually thin crust. It also demanded a complete ascent from ground that could not call Earth directly. Each stage depended on the bridge overhead. The quiet landscape had become connected, but only by design. Remove the relay, and the lander would still function locally. Its words would have nowhere to go. That separation gives far-side exploration its special rhythm. Machines work in sunlight below. A satellite curves through black space above, carrying a narrow stream of instructions and results. In 2024, that stream included confirmation that a drill and scoop had filled a sample container. Soon the container rose from the surface. The far side was about to leave the moon. Chang'e 6 launched on May 3rd of 2024. Its stack included an orbiter, lander, ascent vehicle, and return capsule. The mission had to perform several linked flights. It entered lunar orbit and prepared its descent. On June 2nd, the lander reached a basalt plain in southern Apollo Basin. The selected site sat inside the enormous South Pole Aitken structure. A drill reached below the immediate surface. A robotic arm scooped loose material. Cameras watched the collection area, while instruments recorded local conditions. The samples entered a sealed container. On June 4th, the ascent vehicle lifted from the far side. Its engine raised a small craft against lunar gravity, without a launch tower. The ascender met the orbiter in lunar orbit. Their docking transferred the container. Later, the return craft left lunar space and approached Earth. Near home, the capsule separated. It entered the atmosphere behind a heat shield and landed on June 25th. Search teams recovered it from Inner Mongolia. The sealed material was taken into controlled laboratories. Its total mass was 1,935.3 grams. Early descriptions noted that it appeared clumpier than Chang'e 5 soil. Before distribution, curators documented the container and its seals. Material from the drill could be kept distinct from surface scoops. That separation preserves depth information. Handling happens through clean equipment. A glove box can hold dry nitrogen around the sample. Witness plates and blank controls reveal contamination introduced during work. Earth's air contains water, oxygen, organic compounds, and industrial particles. Each could mask a faint lunar signal. Clean curation is part of the measurement. Density measurements supported that impression. The bulk soil was unusually loose and porous in one initial analysis. Its grains formed a mixture rather than one uniform population. By number, most measured particles were only a few micrometers across. Their mass was concentrated in somewhat larger grains. Glass made up a large fraction of the sample. Impact melts can produce glass. So can volcanic processes. Microscopic texture and chemistry help separate the sources. The local bedrock was basalt. Basalt forms when molten mantle material rises and cools at the surface. Isotope dating placed the dominant local basalt near 2.83 billion years old. Scientists used more than crater counts for that result. Tiny mineral phases preserve uranium, lead, and other isotope systems. Argon released during controlled heating can provide another volcanic clock. Agreement between methods raises confidence. Disagreement can expose later heating, impact mixing, or inherited crystals. The difficult grains often carry the most geological information. That alone changed the far side timeline. Volcanism there remained active far later than a simple early shutdown. A smaller number of basalt fragments dated near 4.2 billion years. The two groups point to widely separated eruptions. More than 1 billion years lay between them. The Moon's volcanic life had pauses, regions, and different sources. The younger basalt carried little titanium compared with many near-side basalts. Its trace elements suggested a mantle source depleted in several incompatible elements. Those elements usually prefer melt over solid crystal during partial melting. Researchers modeled the temperature at which the source melted. Their result placed the far side source roughly 100 degrees Celsius below comparable near-side sources. Remote sensing of the same lava unit supported a smaller but related difference. The sample also held a magnetic memory. Magnetic minerals can align as lava cools through certain temperatures. The direction and strength retained in a rock can reveal an ancient planetary field. Measurements from Chang'e 6 basalt indicated a field around 5 to 21 microteslas at about 2.8 billion years. Modern Earth's surface field is commonly several tens of microteslas. The old lunar field was weaker, but still present. That result suggested a renewed or sustained lunar dynamo after an earlier decline. A small core was still moving enough conductive fluid to generate a global field. The mechanism and duration remain under study. Water offered another contrast. Scientists measured hydrogen in minerals and glass to estimate the source mantle's water. The result was very dry compared with many near-side samples. One study placed the inferred far-side mantle water abundance near the low end of lunar estimates. A small sample from one site cannot represent an entire hemisphere. The result is a local clue, not a global verdict. The same caution applies to heat and magnetism. Apollo Basin is unusual. It lies inside a colossal impact structure and contains mixed ejecta. Every grain needs provenance. Local basalt may have cooled nearby. A pale clast may have flown hundreds of kilometers after another crater formed. Researchers combine mineral chemistry with orbital maps to trace likely origins. A ray crossing the landing site can identify a source crater. Age and texture can support or reject the path. Ancient Norite fragments gave the Great Basin a new age, near 4.25 billion years. The proposed rocks formed in the impact melt sheet and were later excavated again. They turn one basin into a point on the early solar system clock. Other fragments recorded magmatic activity before or around that era. Some formed between 4.34 and 4.31 billion years ago. The mixture reaches back toward the Moon's first crust. Sample return makes such distinctions possible. A rover spectrometer sees broad mineral bands. A laboratory can examine one crystal with an ion beam smaller than a dust mote. Different teams receive tiny allocations. One fragment may be mounted, polished, imaged, heated, or dissolved. The overall collection is protected for later instruments. A polished section can show crystals interlocking at micrometer scale. An electron beam maps elements. A mass spectrometer separates isotopes by weight. Magnetic tests require extra caution because tools and storage fields can alter weak signals. Researchers measure orientation where possible and test whether heating or alternating fields remove later overprints. Water analysis faces its own contamination risk. Hydrogen is common on Earth and scarce in many lunar minerals. Blanks and standards must be measured beside the sample. Apollo samples have continued producing results for more than half a century. Some were stored unopened until modern methods became available. Chang'e 6 material will likely follow the same long arc. The sample container held no single object that answered every mystery. It held a population. Science advanced through distributions, ratios, and disagreements between grains. This is less theatrical than a strange structure in a photograph. It is more durable. A measured isotope ratio can be checked by another laboratory. The result also honors the tidal question directly. What was found on the far side was a cooler and drier mantle source at one site. Ancient and extended volcanism, a magnetic field that persisted, and basin material old enough to reset lunar chronology. None of those findings requires secrecy. The papers describe methods and uncertainty. New analyses can revise individual numbers without erasing the achievement. The dust came home from a hemisphere, once represented by a blurred photograph. Under laboratory light, its grains became clocks and thermometers. Their combined message points inward, toward the Moon's uneven mantle. Heat inside a rocky world comes from several sources. Formation converts collision energy into warmth. Dense material, sinking toward a core, also releases energy. Radioactive isotopes add a slower supply. Potassium, uranium, and thorium decay over immense spans. Each decay contributes a tiny amount of heat. Concentrate those elements in one region, and that region cools more slowly. The near side's Procellarum creep terrain holds elevated amounts of several heat-producing elements. Its location overlaps much of the ancient mare volcanism. Heat moves through rock by conduction when the interior is mostly solid. Temperature differences drive energy toward the surface. A thick insulating crust slows that escape. Earlier, when more mantle was hot and soft, slow convection could move material. The moon's smaller size let it cool faster than Earth. Its internal circulation weakened sooner. An uneven heat source can outlast active convection. Radioactive decay continues in place. The warm province then remains as a deep memory rather than a churning ocean. This relationship is suggestive, but direction matters. An early process may have placed creep on the near side and caused more lava. A larger event may instead have gathered both the elements and the volcanic pathways. One proposed chain begins with the moon's magma ocean. As common minerals crystallized, incompatible elements remained in the last liquid. That leftover material became enriched in creep components. The late melt formed a chemically distinct layer. Later overturn and impacts could move it. The prosolarum region then retained more internal heating. Warmer mantle is easier to melt. Rising melt can exploit fractures left by impact basins. Once lava reaches a low surface, it can spread across enormous areas. The near-side crust is also generally thinner. Less rock separates melt from the surface. A basin impact can reduce the barrier further. The far side combined thicker highlands with fewer heat-producing elements. Its mantle source cooled more. Melt generation became less common. This broad picture fits many observations. It does not explain why the original imbalance began. Several early events remain possible. A giant impact on the near side could have stripped or rearranged crust. Simulations show that some impact sizes and angles can reproduce parts of the thickness pattern. The model must also preserve the far side and match basin ages. The South Pole Aitken impact itself may have moved material across the moon. Its shock could send heat and melt toward the opposite hemisphere. Some studies connect it with the compositional province on the near side. Other models reverse the location of the key event. A large near-side impact creates the dichotomy directly. Different simulations can produce similar final maps, which makes samples important. An old companion moon offers a quieter collision. In that idea, Earth once had two moons. The smaller one merged slowly onto one hemisphere and thickened its crust. The model can make a broad highland bulge. It must also fit orbital motion and chemical evidence. No surviving fragment announces that it came from a former moon. Early Earth provides another source of asymmetry. The newborn moon orbited much closer than it does now. Earth would have filled a large part of its sky. The post-impact Earth was extremely hot. Radiation from its molten surface may have warmed the lunar near side. The far side could cool and crystallize first. Earlier crust on the far side might grow thicker. Volatile and heat-producing elements might condense differently. The facing hemisphere could remain thinner and warmer. This idea joins orbital locking with thermal history. It depends on when the moon became locked, how hot Earth remained, and how rapidly the lunar magma ocean cooled. Each timescale carries uncertainty. Tides offer another source. A young moon on an eccentric orbit flexed more strongly than it does today. Internal friction turned that flexing into heat. If structure or orbital geometry made the heating uneven, one hemisphere could evolve differently. Near and far side asymmetry in a tidally heated moon has been modeled. Again, several initial conditions can lead toward the observed pattern. The 2025 Grail analysis did not choose one origin story. It showed that a deep difference still exists. The moon's tidal response contained a degree 3 pattern consistent with a warmer near-side mantle. Degree describes a broad spatial pattern in a spherical field. Low-degree terms span large fractions of a globe. A degree 3 feature is therefore not a small hot pocket beneath one crater. Researchers had to separate the tidal signal from static gravity, orbital effects, and measurement noise. Long records helped. Ebb and flow repeatedly sampled the changing pull. The result constrained magnitude and location, but not a unique cause. Several histories can leave a similar present temperature structure. Geology supplies the missing time order. The inferred anomaly was roughly 100 to 200 kelvins. Kelvin and Celsius degrees have the same size, so the temperature difference has the same numerical range. The 0 points differ, but differences do not. The signal comes from how gravity changes through the monthly tide. Earth stretches the moon slightly. Warmer mantle yields more than colder mantle. The deformation is tiny. No eye can see the body breathe. Precise tracking of spacecraft reveals the change. The sample result then added a point measurement from the past. Chang'e, 6 basalt crystallized from a cooler source than near-side basalts. A rock and a gravity field were telling compatible stories. Compatibility is not identity. The sample records conditions when its magma formed. Grail reads the present interior response. The link requires models of cooling over 2.8 billion years. If the asymmetry persisted, its origin had to survive convection, impacts, and gradual heat loss. The moon's small size helped its interior become relatively still. Modelers vary element abundance, mantle viscosity, crustal thickness, and starting temperature. A successful run must produce lava at the right ages and places. It must also end with today's gravity response. Samples give fixed points within that moving model. A basalt age says melt existed then. Trace elements constrain how much melting occurred and what source produced it. The final explanation will likely be a range of histories rather than one exact animation. Uncertainty can narrow without disappearing. Deep moonquakes may also feel the difference. Tidal stresses trigger some clusters at repeated locations. Their distribution could reflect variations in temperature and structure. Future seismometers on the far side would improve the picture. Apollo instruments all sat on the near side. A global network could measure waves passing through the whole body from several directions. Heat flow instruments would add another line. The Apollo heat flow sites were both on the near side and may not represent the moon. A far side measurement could test the predicted contrast directly. New samples from far side highlands would also help. Chang'e seeks collected within a basaltic and impact mixed setting. A pristine highland site could sample the older crust. The hemispheres, therefore, remain an active experiment. Their difference is obvious to a camera and subtle to a model. Each new instrument moves the explanation from appearance toward cause. Above that uneven interior, the surface follows a simpler rule. Sunlight arrives. Heat rises quickly in the exposed soil, then escapes through the long night. Weather on Earth is moving air and water. The moon has neither in useful surface amounts. Its environment changes through light, heat, radiation, and falling debris. Near the lunar equator, daylight can raise surface temperature above 121 degrees Celsius. After sunset, the same region can fall near minus 133 degrees Celsius. The ground crosses that range over a slow lunar day. The far side follows the same broad pattern. Its direction from Earth does not change the sunlight it receives. Latitude, slope, local time, and surface material control temperature. A sunlit rock can become hot while nearby shadow stays cold. Almost no atmosphere carries heat sideways. Each surface exchanges energy mainly with sunlight, the ground below, and open space. The lunar atmosphere is an exosphere. Its particles are so sparse that collisions are rare. NASA describes it as holding about 1,000,000 billion times fewer molecules per cubic centimeter than Earth's atmosphere. The exosphere contains helium, argon, neon, sodium, and potassium, among other species. Some atoms come from solar wind, radioactive decay, impacts, or release from soil. They follow long ballistic arcs rather than flowing as ordinary wind. Many escape to space or return to the surface. Density changes with local time and meteor showers. An astronaut would not feel those particles as air. Instruments detect them through light, mass, or charged interactions. No breeze lifts dust across a plain. No cloud softens noon. A black sky remains above the sunlit ground because there is too little air to scatter blue light. Shadows keep sharp borders. Inside them, a slope may disappear into blackness. Sunlit grains beside the edge can shine almost white. The top layer is regolith. It is a mixture of mineral fragments, glass, and tiny bonded clumps called agglutinates. Continuous impacts created it from once solid rock. Regolith also controls temperature. Its upper grains touch at few points, so heat moves poorly between them. Daytime warmth does not travel deep quickly. Several centimeters below the surface, the daily swing becomes smaller. Deeper ground changes more slowly. A buried instrument experiences a gentler thermal cycle than one exposed above. Color and grain size matter. Dark basalt absorbs more sunlight than pale highland material. Slope determines whether rays strike directly or skim across the ground. Micrometeorites arrive at high speed. Even a grain can release enough energy to melt a speck of soil. The melt cools into glass and can weld smaller particles together. Larger impacts throw rays and blankets across the ground. The ejecta churns older material upward. This mixing is called impact gardening. Gardening is slow by human standards. Across billions of years, it can turn solid crust into meters of broken material. Deeper layers preserve older events with less exposure. The far side receives impacts from the same surrounding populations as the near side. Small differences in direction and orbital motion can affect flux. Recent sample work studies whether those differences leave measurable weathering patterns. Solar wind is another sculptor. It is a flow of charged particles from the sun. Ions strike exposed grains and disturb their crystal surfaces. Some particles implant hydrogen, others knock atoms free. Over time, nanometer-sized iron particles can form and change how soil reflects light. Earth's magnetotail changes the plasma around the moon during part of each month. Exposure can differ with hemisphere, terrain, and magnetic anomalies. Chang'e. 6 grains show weathering features that may reflect stronger solar wind influence. Researchers compared damaged rims, tiny iron grains, and impact melt on returned particles. Their work suggested solar wind played a larger role at the sampled far side site. The conclusion remains limited by one mixed collection. Space weathering can make old ground darker and redder in reflected light. A fresh crater exposes brighter material. Its rays fade gradually as new exposure changes the grains. This is why young craters appear bright in orbital images. The brightness does not require ice. It often marks less weathered rock. Radiation reaches beyond the grain surface. Galactic cosmic rays include atomic nuclei traveling near light speed. Solar particle events can deliver sudden doses. Chang'e 4 carried a detector on the far side ground. It measured charged particles and secondary radiation. The instrument helped describe the dose environment future crews would face. The lunar soil itself creates secondaries. High-energy particles strike nuclei in the ground. Neutrons and gamma rays can scatter back upward. A habitat would need shielding from several directions. Regolith piled over a structure can help. Water and other hydrogen-rich materials can also slow some particles. The surface gives no reliable visual warning of a solar event. Space weather monitors and forecasts become part of lunar weather. A calm black sky can carry dangerous particles. Temperature is another engineering limit. Batteries and lubricants have operating ranges. Electronics may need insulation, heaters, radiators, and periods of rest. U-22 sleeps through the lunar night because solar power disappears. Chang'e 4's systems use thermal control to survive. Waking after 2 weeks of cold is a repeated test. Dust adds a mechanical problem. Lunar grains have sharp edges because water and wind do not round them. Electrostatic charge can make fine particles cling to surfaces. Apollo crews found dust on suits and seals. A far side crew would meet the same abrasive material. Local composition may change color and texture, but the hazard is lunar-wide. Static fields change as sunlight reaches the surface. Ultraviolet light can release electrons. Plasma from the solar wind supplies other charges. Scientists continue studying whether tiny grains loft briefly near boundaries between day and night. The effect is difficult to measure. It should not be imagined as a thick, floating fog. The ground can also shake. Deep moonquakes respond to tides. Shallow quakes, thermal cracking, and impacts produce other signals. Thermal cracking works slowly around sunrise and sunset. Rock expands under light and contracts in cold. Repetition opens small fractures. An impact makes a sharper pulse. With no nearby traffic or ocean noise, a sensitive seismometer can detect distant events. The fractured crust then scatters the waves. Without oceans and active plate boundaries, lunar quakes differ from terrestrial earthquakes. Dry, fractured rock can let vibrations ring for longer. Apollo instruments compared the moon's response to a bell. No seismometer has yet built a complete, long-lived, global far-side record. A network across both hemispheres would locate events more accurately. It would also map deep structure. Every environmental effect leaves a timescale. Heat changes across days. Radiation can spike within hours. Impact weathering accumulates across millions of years. Basin scars endure for billions. The far side holds all those clocks in one quiet surface. At sunrise, the first light touches elevated rims. Low ground remains black until the solar angle climbs. A thermal front follows the illumination across exposed grains. Instruments can watch that change through infrared emission. Warmer material radiates more strongly. Differences after sunset reveal how quickly each surface stored and released heat. A blocky ejecta field cools differently from fine powder. Young craters often show unusual nighttime warmth. Their rocks have not yet been ground completely into fine regolith. The pattern provides another age clue beside brightness and crater count. The long night also changes electrical conditions. Without ultraviolet sunlight, photoelectric charging weakens. Plasma around the moon then shapes surface potential differently. Charging matters for sensitive electronics and dust. A voltage difference can form across shadow boundaries. Engineers test materials for arcing and adhesion. The effect is invisible to an unprotected eye. No colored curtain hangs over the ground. Instruments measure particles and fields directly. Inside a habitat, life support would create an artificial Earth-like pocket. Air would carry heat, fans would move sound, and filters would catch dust. Outside the wall, the exosphere would remain almost empty. Every exit would join those environments through an airlock. Dust control would begin before the outer hatch closed. Brushes, seals, electrostatic systems, and suit ports are all possible tools. The far side adds no special airless physics. Its value comes from where that physics has acted on different rocks. Returned grains allow near and far side weathering to be compared under microscopes. Its radio environment adds another kind of weather. Signals from Earth rise and fall with geometry. Behind the moon, much of the artificial radio sky becomes calm. Earth is bright in radio wavelengths. Broadcast transmitters, radar, satellites, navigation systems, and electronics add signals across many bands. Lightning and auroras add natural emissions. The atmosphere creates a second limit. Earth's ionosphere reflects or distorts very low-frequency radio waves from space. Ground telescopes cannot observe some of the longest cosmic wavelengths cleanly. The lunar far side sits beyond that ionosphere. The Moon's body can also block direct radio interference from Earth. Together, those conditions make part of the far side unusually quiet. Quiet does not mean silent at every frequency. Radio waves can diffract around the lunar limb. Satellites above the surface can carry interference into view. The protected region changes with altitude and frequency. A telescope deep within central far side terrain receives better shielding than one near the limb. Local transmitters would still be close and strong. Researchers model how radio waves bend around the Moon. Measurements and simulations show heavy attenuation in selected regions. The result has inspired the idea of a shielded zone. The International Telecommunication Union recognized a protected area behind the Moon decades ago. Coordination can reduce harmful transmissions there. Legal and technical protection becomes more important as lunar traffic grows. The science target lies far back in cosmic time. Before the first stars, neutral hydrogen-filled expanding space. That gas could absorb or emit radiation with a rest wavelength of 21 centimeters. Expansion stretched the ancient signal to much longer wavelengths. By the time it reaches modern instruments, some of it lies at frequencies difficult or impossible to study from Earth's ground. A far-side array could search that region. Scientists call the early interval the cosmic dark ages. The name describes a universe before starlight, not the lighting of the lunar surface. Hydrogen still carried information through radio signatures. Later, the first stars and galaxies heated and ionized surrounding gas. Their appearance changed the hydrogen signal. Mapping that change would constrain when cosmic dawn began. The expected signal is faint. The Milky Way's foreground radio glow is vastly stronger. Human transmitters can be stronger still. Long wavelength does not mean loud sound. Radio is electromagnetic radiation. Antennas convert changing electric fields into signals that computers can analyze. At lower frequency, efficient antennas become physically longer relative to the wavelength. Thin dipoles can lie across the ground instead of standing as dishes. The array may look like dark lines unrolled over dust. Each element records voltage over time. Correlation between pairs preserves information about direction. Many pairs turn a sparse field of wires into an image-forming instrument. An array needs many antennas. Their signals combine through interferometry. Precise timing turns separation across the ground into a much larger virtual instrument. One studied concept called Farside uses 128 dual polarization antennas across about 10 kilometers. A rover would unroll thin tethers on the surface. The design remains a concept, not an operating observatory. The central electronics would digitize enormous streams of data. Much of the first processing must happen locally. Sending every raw sample through a relay would demand too much bandwidth. Calibration sources help measure how each antenna responds. Temperature changes alter cables and amplifiers. Dust and terrain can affect the electrical ground. An array must know its own shape precisely. Rover placement errors can be measured after deployment. Star signals then help refine the geometry. Another concept imagines far more dipoles manufactured partly from lunar material. Its scale reaches hundreds of square kilometers. That proposal is even farther from construction. Small Pathfinder instruments come first. The Chang'e 4 lander carried a low-frequency spectrometer. Quietest carried a Netherlands-China low-frequency explorer with antennas deployed in space. Orbiting and surface instruments face different noise. A spacecraft moves in and out of Earth's radio shadow. A ground array can remain protected, but must survive lunar temperature cycles and dust. The long night can help some observations. The sun is a powerful radio source. When the far side site is also on the lunar night side, both Earth and direct solar emissions can be reduced. Night removes solar power. Batteries or radioisotope systems must support the instrument. Thermal control must keep electronics alive through deep cold. The radio shield also complicates data return. A telescope protected from Earth cannot send data straight to Earth. A relay must receive the information without flooding the observatory with interference. Engineers can separate observing and communication periods. Directional antennas and distant relays can reduce local noise. Hardware can be designed for electromagnetic cleanliness. The problem resembles a library beside a road. Closing the road creates quiet, but books still need delivery. Every vehicle and lamp must be managed. Far-side radio astronomy is not only about the early universe. Low frequencies can study solar eruptions and planetary magnetospheres. They may also reveal energetic activity around nearby stars. Some proposed arrays would monitor the whole sky repeatedly. A stellar radio burst could indicate conditions affecting an exoplanet. Such measurements could inform ideas about atmospheric loss and habitability. Signals from auroras around exoplanets are another possible target. Detection would be difficult. No promise of an easy result should be attached to it. The strongest case for the far side is access. Certain frequencies are screened from Earth by the ionosphere. There are few nearby places where a stable surface and natural radio shield exist together. Below roughly 10 megahertz, Earth's ionosphere becomes especially restrictive. The exact cutoff changes with time and conditions. Space-based instruments avoid it. At higher frequencies, ground observatories work well from remote deserts. The far side advantage is greatest where Earth itself cannot offer a clear window. That keeps the lunar case focused. Foreground removal remains necessary even in perfect radio quiet. The galaxy fills the sky. A cosmic dawn signal must be separated through its spectrum and spatial pattern. Free-flying arrays in space offer another route. They avoid lunar dust and landing. They must maintain formation and process data without a solid ground plane. The far side provides ground, shielding, and long baselines. It also provides gravity, night, rough terrain, and political questions. Scientific value does not erase engineering cost. Protection may become the hardest part. Relay satellites, Navigation transmitters, habitats, and vehicles will need radio links. Poorly planned systems could spoil the very quiet that makes the region rare. The choice is not between exploration and silence. Frequency allocation, antenna placement, timing, and shielded corridors can support both. Early standards are easier than later repair. Apollo 8 and Artemis II demonstrated the block in human terms. Their temporary radio loss was a mission event. For an observatory, the same loss becomes shelter. Across the central far side, Earth never enters the local sky. A telescope there would work beneath stars and a moving sun. The home planet would be present only through the relay. That absence can feel complete, but sunlight still divides the ground into day and night. Near the poles, another geometry makes some shadows truly permanent. The moon's spin axis is tilted only slightly relative to its path around the sun. Near the poles, sunlight moves close to the horizon. Tall crater walls can block it year after year. Some crater floors never receive direct sunlight. They are called permanently shadowed regions. Their darkness is based on local terrain and polar geometry. Permanent is used across long astronomical times, not as a guarantee that every atom remains fixed forever. Small changes in the moon's orientation and impacts can alter edges. The deepest central zones remain the most stable. Computer illumination models trace the sun across years. Laser topography supplies each ridge and hollow. A pixel that never receives a direct ray becomes a candidate permanent shadow. Scattered light can still enter. Starlight and reflected glow from nearby slopes are extremely faint. They add little heat compared with direct sun. These regions exist on both near and far side portions of the poles. They are distinct from the whole far side. Most far side ground receives long days of full sunlight. Inside selected polar shadows, temperatures can fall below -246 degrees Celsius. NASA's Lunar Reconnaissance Orbiter measured such extremes with the Diviner instrument. They rank among the coldest measured surfaces in the solar system. At those temperatures, a molecule of water can remain trapped for immense spans. Other volatile compounds can freeze too. The shadow becomes a cold trap. Temperature controls residence time sharply. A small increase can let molecules escape a grain much sooner. The coldest floor can retain species that a warmer shadow loses. Different volatiles freeze at different conditions. Water is only one member of the mixture. Carbon-bearing and sulfur-bearing molecules can reveal distinct sources. Sunlight at a shadow edge can release material that settles deeper inside. The crater becomes a landscape of chemical sorting. Water may arrive in several ways. Comets and water-bearing asteroids deliver some. Solar wind hydrogen can react with oxygen in lunar minerals. Small impacts can move or release molecules. Heat from sunlight lets them hop across the surface. A molecule that reaches a deep, cold trap may stay. Orbital neutron measurements found extra hydrogen near the poles. Radar and infrared observations added evidence. An impact mission called L-Cross excavated material from Cabeus crater and detected water and other volatiles. The deposits are not clear lakes under smooth ice. Water can be mixed through soil, concentrated in patches, or bound in grains. Its abundance varies by location and depth. Some sunlit soil also contains small amounts of water, or hydroxyl. These molecules can change with local time. The polar archive is only one part of lunar water science. South Pole Aitken reaches toward the lunar South Polar region, but the terms are not interchangeable. The basin covers a vast far-side area. Permanently shadowed craters occupy much smaller pockets near the pole. The Chang'e 6 landing site was around 42 degrees south. It was not inside a permanent polar shadow. Its samples came from sunlit basaltic ground. This distinction prevents a common error. Far-side sample dryness does not prove that polar ice is absent. Mantle water and surface cold trap ice have different histories. The water inferred from basalt concerns the rock's deep source. Polar ice may have arrived later from impacts or solar wind. One can be scarce, while the other remains locally useful. Cold traps preserve more than water. Carbon dioxide, ammonia, sulfur compounds, and organic molecules may freeze under suitable conditions. Their mixtures could record delivery through solar system history. A core from a shadowed deposit might hold layers from different eras. Interpreting those layers would require great care. Impacts mix soil, and molecules can migrate. The scientific archive is also a possible resource. Future crews could process water for drinking, oxygen, or propellant. Every use would need prospecting first. An orbital hydrogen map cannot tell an engineer how an excavator will behave. Grain size, concentration, hardness, slope, and lighting all matter. A deposit may be valuable and difficult to reach. Extraction also changes the archive. Heating soil releases volatiles, but it can erase their original arrangement. Science teams may want untouched cores before large-scale processing begins. Resource planners need abundance per unit mass, not only presence. A trace detected from orbit may require moving too much soil. A concentrated lens could be far more useful. Transport adds another cost. Water recovered in a deep crater must climb to equipment or a launch site. Energy, insulation, and storage shape the real value. The thermal environment is severe. Machinery enters a shadow and loses solar heating. Batteries cool while direct communication may be limited by terrain. Crater floors can hide boulders and steep walls. Low sunlight creates long shadows around the rim. Navigation must work with high contrast and incomplete views. Some high polar ridges receive sunlight for long periods. They are not peaks of eternal light, but they can offer better power conditions. A base might connect bright ridges with nearby dark science sites. The boundary between light and shadow is narrow. A rover can move from warmth into extreme cold over a short distance. Materials contract, and frost can alter surfaces. The coldest ground is measured remotely. Diviner senses emitted infrared energy. At very low temperatures, the signal is faint, and models infer the surface condition. Laser altimeters help map the shape of darkness. A laser supplies its own light and times the return. It can measure terrain even where the sun never reaches. LRO has used years of repeated passes to improve polar maps. Different lighting and viewing angles reveal hazards. Future landers add local measurements. The far side contributes its own polar terrain. South Pole Aitken altered elevation and crust around the south. Ancient impact materials may lie near future exploration zones. A sample from a cold trap could answer questions about incoming water. A sample from a basin ejecta field could date the oldest impacts. Nearby sites can hold very different archives. Choosing a route becomes a choice between histories. One path follows sunlight for power. Another enters darkness for volatiles. The moon offers no weather forecast in the earthly sense. The sun's angle can be predicted precisely. A crater's shadow can be mapped. The uncertainty lies in the ground. Ice may occur in lenses, grains, or scarce patches. One drill can turn a colored orbital map into a measured column. This is the same movement that shaped far-side science as a whole. First came a brightness pattern. Then came height, gravity, chemistry, and finally returned grains. Many measurements are still missing. The far side waits for a seismic network, direct heat flow, more sample sites, and a protected radio observatory. Each would read a different layer. Coordination will matter because no one mission owns the full question. Orbital maps from several nations already overlap. Returned grains can be studied by laboratories with different strengths. Shared standards let gravity, imagery, spectra, and surface coordinates align. Open archives allow a future team to compare a new crater with records collected decades earlier. The moon's history is global even when a sample belongs to one mission. An age from Apollo Basin can improve crater clocks used across the solar system. A far-side heat flow value can correct models built from near-side sites. The next decisive instrument may be a seismometer. Apollo's network listened from the near side. It discovered deep moonquakes, shallow events, impacts, and the moon's long ringing response. A far-side station would widen the network across the globe. Waves could cross the core and mantle along new paths. Differences in arrival time would sharpen maps of the interior. Several stations would be better than one. Event location requires geometry. A signal reaching separated instruments becomes a position and depth. The data could test the deep thermal asymmetry. Warmer rock changes seismic speed and attenuation. A network might show how far the near-side anomaly extends. Heat flow offers a second direct test. A probe can bury temperature sensors at several depths. The gradient reveals energy escaping from below. Apollo's successful heat flow measurements came from two near-side sites. Both lay within or near the geochemically unusual Procellarum region. They may overstate the global average. A far-side highland site would provide the missing contrast. It could test whether the mantle and crust release less heat there. Sample chemistry and Grail would gain a direct local partner. New sample returns can separate terrain types. Chang'e brought basalt and mixed basin ejecta. A highland collection could represent the ancient crust more cleanly. A carefully chosen South Pole Aitken traverse could gather rocks across several geological units. Each sample would need documented position and context. A bag without a map loses much of its story. The basin age, near 4.25 billion years, is strong evidence, yet replication matters. More impact melt from different locations could confirm it. Unexpected ages might reveal separate events. Drilling below the churned surface would reach material with less recent exposure. Layers could preserve solar particles, impact debris, and ancient volcanic deposits. Depth turns a mixed surface into a rough timeline. Radio astronomy requires a different kind of patience. A pathfinder array could first measure the true interference environment. It would map quiet by frequency, location, and lunar time. The result could guide larger antennas. It could also identify which satellite links cause trouble. Protection would be built from measurements rather than hope. Human exploration may bring the most visible changes. Artemis II has already carried people around the far side again. Its photographs placed Earthset beside a new generation of lunar maps. Future crews could orbit, relay, and perhaps work near southern terrain. Surface plans will continue changing with budgets, testing, and safety. Scientific priorities can remain steady through schedule changes. Robotic missions can arrive first at sites too cold, steep, or radio quiet for routine crews. People can later service instruments, select complex samples, and respond to unexpected geology. The two approaches do not compete. A relay maintained by one mission can support several others. A crewed vehicle can carry small scientific packages that continue after departure. Long-lived infrastructure must also avoid contaminating delicate measurements. Power systems, exhaust, dust, heat, and radio emissions all need site planning. Those priorities include old crust, basin melt, polar volatiles, deep structure, and radio quiet. No single landing site reaches all of them. A network of missions will be needed. The far side also needs restraint. Tire tracks and landing plumes can disturb local ground. Radio transmitters can spread far beyond a landing pad. Some places may deserve protected status before equipment arrives. An undisturbed cold trap holds a chemical archive. A central radio quiet zone holds an environmental one. Protection does not make the moon untouched. Impacts continue, and solar wind continues. It keeps human activity from erasing a condition that cannot be rebuilt easily. The hidden hemisphere is close enough for light to reach Earth in a little more than 1 second. It is far enough for a body of rock to block every direct signal. Distance alone does not define remoteness. Geometry does. A person in central far-side terrain could never look up and see Earth. Home would remain beneath the horizon, while the sun moved slowly across black sky. The relay would make Earth present through data. A small antenna would carry voices over the moon. Without it, the same terrain would return to radio separation. That contrast has followed the story from the beginning. Luna 3 entered silence to expose film. Apollo 8 crossed silence with 3 people aboard. Chang'e 4 bridged silence with Quietest. Chang'e 6 carried soil across it. Artemis II watched Earth set, then waited for it to rise. Each mission found less secrecy and more structure. Craters gained names. Height maps gained gravity. Spectra became minerals. Minerals became dated grains. A visual difference became an internal temperature difference. The main mystery remains open in a productive way. Scientists know several mechanisms that shaped the two faces. They do not yet know the exact order and weight of every cause. The answer may be layered rather than singular. Early Earth could affect crust formation. Impacts could redistribute material. Radioactive elements could sustain near-side heat. Thicker far-side crust could limit eruptions. Later basins could overprint the first pattern. The layered answer is not a retreat from clarity. It is how planetary history often works. One event sets an initial difference, and later processes enlarge or preserve it. Finding the first cause requires the oldest material. Measuring later amplification requires younger lava and present heat. The far side holds both in neighboring terrains. That is why one more sample can matter after global mapping. A map shows correlation. A dated rock puts an event on the clock. A world can carry several causes at once. The useful task is to measure how much each contributed. Future rocks and waves will narrow the range. For this night, the returned grains can settle again in their clean containers. The relay can move silently along its wide curve. Long shadows can cross von Karman one small degree at a time. The sensory record remains simple. Pale highlands hold sharp rims. Dark basalt lies in rare, quiet pools. Glass grains rest among powdered stone. A rover track passes between small craters and stops at the edge of its latest plan. Far above, Earth is absent from the local sky. Beyond the limb, it remains blue, clouded, and near in light time. That hidden blue world gives the story its tender scale. Every map, relay, sample box, and returning capsule began there. Curiosity crossed the boundary because people built careful ways to carry it. The moon did not keep its far side as a secret. Gravity simply held one face home. Human sight needed time to reach the other. Now the old blank area has weather, ages, minerals, and names. It has the soft gray dust of basalt and the pale fragments of a crust formed near the beginning. There is gratitude in that slow correction. A blurred frame became a globe. A globe became a place where one small rover could leave parallel lines. The night can release the remaining questions. No answer is required before rest. The moon will continue its matched turning without attention. Its near side can face the sleeping Earth. Its far side can receive the same sunlight in another phase. Between them, no edge exists. Only one round world remains, carrying two histories through the dark. The relay passes overhead. The ancient basin cools beneath it. The room is still. The last blue crescent sinks beyond the lunar horizon, and the radio grows quiet. Good night.